Hello once again. We're going to be continuing on with the 2014 Cimc, that's the Canadian Intermediate Mathematics Competition, and we're going to be looking at question number 6. So a positive integer is a prime number if it is greater than 1 and has no positive divisors other than 1 and itself. For example, the number 5 is a prime because it's greater than 1, which they don't mention, and because it's only got 2 positive divisors, namely 1 and 5. Okay, so this is going to be a prime number style question. Alright, the integer 43,797 satisfies the following conditions. Each pair of neighboring digits, read left to right, forms a 2-digit prime number, and all of the prime numbers formed by these pairs are different. Okay, well we can check that out. 43, definitely prime. 37, that's prime. 79, that's prime. And 97, that's prime. Oh, okay, they go ahead and mention that anyway. There are many integers with more than 5 digits that satisfy both these conditions. So each pair is 2-digit primes, and all of the prime numbers are different. What is the largest positive integer that satisfies both these conditions? So right off the bat, I see the pairs are different is kind of important. Otherwise, you could just do 1, 1, 1, 1, 1, 1, because it'd be 11 and then 11 and then 11. But they want different primes. Okay. So a good thing to do might be to start off by listing all the 2-digit primes, because those are the ones we're going to need to sort of smoosh together to create a large integer. Okay. So, prime numbers are something that you should hopefully be familiar with at this stage in your education, but if not, this question might be rather difficult, just because we are going to have to go through and list all the primes, and you don't want to have to figure them out with your calculator. I mean, there are a couple that you can, that people tend to screw up, but you want to be well-versed in your prime numbers for this question. So let's list out our prime numbers. For 2 digits, I usually start at 100 and go backwards, but you can do it however you want. So 2-digit primes. Starting at 100, 97, and that's a prime number. 95, no. 99, no. That's 93, no. 91 is not one. 7 times 13. I imagine that will probably trip a lot of people up. That one doesn't come up a lot, and it's not immediately apparent that... you know 93 isn't a prime, because 93 is divisible by 3 just by looking at it. 9 and 3, they add up to 12. That's divisible by 3. So this one is not a prime, but I imagine it would catch a lot of people. Okay? Just like 51 might catch some people. So that's 91. We go down to 89. 87, nope, divisible by 3. 85, nope. 83, yep. 81, that's one that might catch people, but it's 9 squared, so hopefully that one didn't trip you up. Now we're into 79, sure. 77, that one, nope, that's divisible by 11. 75, nope. 73, yes. 71, yes. 69, nope, that's divisible by 3. 3 times 23. How about 67? Absolutely. 65, nope. 63, nope. 61, yep. Then we go down to 59. 57 is divisible by 3. 53. 51, no, that's 17 times 3. I could see that one screwing some people up as well. So we ignore him. Actually, no point in me writing these if I'm going to erase them or scratch them out, because then no one can see them later. I will add in that 91 is not a prime, but I will do that in red, because I imagine 91 really messed some people up. And we will strike it out, but you can clearly see it's still 91. Alright, back to our list. So 51, that was no. So now we're into smaller ones. Oh, 81, also not a prime. So need to get that guy off the list. I wrote him down as an example of something you shouldn't do, and then I didn't write out what he was what his actual factorization was. So 51, no. 49, that's 7 squared. 47, we'll start up here again. 43, 41, these are all primes. These two are twin primes. 39, no. That's divisible by 3. 37, 35, that's a no. 33, no. 31, 29, that's another pair of twin primes. Then 23. 27 is 3 cubed, so it's 3 times 9. 21, that's a no-go. 19, 17, not 15, 13, and 11, and now we're at the end of the 2-digit primes. Okay. So now we have all our 2-digit primes listed out. So what do we need to do? We need to, well, what exactly is the question asking again? So distinct 2-digit primes, and each pair of neighboring digits forms a 2-digit prime number. And we want to make the largest positive integer that satisfies this. Okay. So, at very best, we could maybe somehow use all these primes. Right? All of these primes, and get a really, really long number. Right? So that would be the best thing we could hope for, is use all these. Unfortunately, we can use at most 1 prime. That starts with an even number. Why is that? Well, suppose we had the number, let's say 83, but it wasn't. It was the second number we've used, the second prime number that starts with an even number that we've used. It will have to be somewhere in the middle of our long string of digits. It'll have to be somewhere in the middle of the number. That means the number before it will have to be something like, I don't know, maybe it's 5 or something. Then you'd have 583 is somewhere in your number. 58, not a prime. So the only place that we can have an even number is at the very, very start of the number. Otherwise, at some point, you're going to have a pair of digits that will be even. Okay, so at best, our number could look like, even number and then a whole bunch of odds. All right. So how about we set aside the even primes? Because if we can just focus on the body here, and we can figure out what this number, maybe this number is forced, and then so we'll have a limited number of even numbers to pick from. Alright, so what were those ones? That was, I'm going to have to pop back to my list because I don't remember them off the top of my head. 79, 73, 71. Then we're down to the 50s, so 59, not 57, but 53, 47. Oh, no. We don't need to do the 40s. We need to jump down to the 30s, so 37. 31, 29. Oh, I did it again. We're not at 29. We only want ones with odd digits. So 19, 17, 13, and 11. So that should be it. So 2, 4, 6, 8, 10, 12 of them. Okay. So at best, I could use all of these maybe. So there really isn't any other direction other than to perhaps try and use all of them. We could try and maximize the number we can use, but really I wouldn't know where to start. Obviously, naively I would start with, say, 97 and then choose 79 to add on to it. But then there's nowhere else for that to go. So then you'd have 9, 7, 9. If you wanted to add more to it, there's no other odd prime starting, or there's no other prime starting with 9 left over. So what I can note is that the end of the last digit of each prime okay. So the end of each prime is the start of the next one. So what could we do? We could try and pair these things up as best as we can. That's the general idea. And then, hopefully that'll go somewhere. So, how many ones do we have that end with 9? How many ones do we have that end with 7? How many ones do we have that end with 3? So, alright, so 9s are sort of at a premium. How many start with 7? So 1, 2, 3, 3. Three start with 7, and 1, 2, 3. And 3 of them end with 7. So 1, 2, 3, yeah. Alright. Now, 2 of them start with 5. But we can ignore these 2, actually. We should likely throw them out, or at least keep them by the same reasoning. Alright, so just like we didn't include 89 because it would stifle our creativity, we should actually throw out these ones that start with 5. So we can ignore, whoops. So we can ignore them, and we can actually go back and redo our lists. Okay. So one of them start with 9. And now 2 end with 9. Okay. How many start with 7 now? Still 3. How many end with 7? Well, still 3. Now we don't need to do 5. How many started with 3? Well, that would be 37 and 31. How many ended with 3? Okay, those I don't know off the top of my head. We're not including 53, so that helps. 73 and 13. So 2 end with 3. How many start with 1? 4 of them. Almost all the teams are prime. How many end with 1? Not 91. 71, yep. Not 51, 31, so... So, looking at things, looks like we could probably match up all the 7s, and we could probably match up all the 3s. We have way more 1s at the start than we need. And we have an extra 9 at the end. So, how about we just write that out? So, right, this will all depend on whether or not things can work out. But in theory, we should be able to match up all the things that start with a 7 and have them come from something that ends with a 7. Okay. All right, we have one extra 9 at the end, so how about we make the whole thing end with a 9? Okay. Oh. No, silly me. 1, 2, 3. I forgot to count 11 when I said. So we have 3 that end with a 1. I'm glad I just caught that. I completely forgot about 11. So. Right? So now we're looking at so we might have an even number or a 5, or we might just have nothing at the start. We don't know. But we've got a 1, and then we've got a whole bunch of stuff, and hopefully we can pair up all the 7s and the 3s and everything like that. and then a 9. Okay? So, other than that, it's time to start pairing. Now, if we go back to our main list, we can probably find 51 can't work, but maybe we can find an even number that does work. So 61, I think. Yeah, 61. So if we start with a 6, we'll definitely be as high as possible there. I mean, we could have a 4, but we're trying to shoot for the highest possible number. All right. So 61, and then we want to get the highest number possible, so we should put the highest number here as possible. If we have a 7 here, when we could have a 9, we're automatically, no matter what the rest of the number is, going to be lower. So we can put the 9 for 19 there. Okay. So if we have a 9, there's only one number that can follow, and that's got to be 7. Okay. Now, we could put 79, but we've used up 19. So this 9 at the end's got to be 79. Okay, it has to be. That's otherwise we won't get it ending in a 9, and we want our integer to end in a 9. So we can't have 79 here. What's the next highest we can have? 73. Okay. Highest that we can go with a 3. That's 7. That forces 71. And we want it to be 17. That's the next highest thing that starts with a 1. But if we do that, we're not going to get this 7 right here. So he's got to be 17. Right there. So what's the next highest? 13. Okay. So if we have 13, then we have to have, so we've had 37. It's got to be 31. All right. So what teens are left? We got 19, 17, 13. We would have to have 11, but that would be exactly this number. So some of you might be wondering, well, how do you know that's the highest integer? Well, look at the steps we took. If you need to, rewind the video and listen to the steps we took. The reason we wanted to get as many numbers, a longer integer is going to be bigger just by virtue of more digits. 10,000 is definitely bigger than 9,800. It just has more digits, so it's automatically higher. So if we can cram as many of these odd 2-digit primes together, if we can cram them all, we definitely know we're at the highest. Failing that, we would have just tried to cram as many as possible. If I hadn't caught that 2 of them end with a 1, we would have had to omit something that starts with a 1, possibly 11. So, the more digits, if this one has the most digits possible, the 6 we chose gave us the highest possible. We could have had 41, but that would have been a smaller number. Why does that keep happening? Right? So using as many digits as possible forced us to have blank 1, a whole bunch of stuff, and then end with a 9. Knowing that 61 was the highest possible. We could add 61, we could add 41, but 61 was highest possible. So that also tells us we're starting to look at the highest possible number. And, yeah. I should probably say not starting with 5. But we couldn't have one that starts with 5 anywhere in there, because otherwise the digit before it, you know, if you had a 7 before it, you'd have 75, not prime. So the number we would put in the box is 6197371311179. That is the highest integer possible with the 2 properties specified in the question. Okay. Each pair of neighboring digits, read from left to right, forms a 2-digit prime number. And all of the prime numbers formed by these pairs are distinct. Okay, we only used every prime at most once, and each pair is definitely a 2-digit prime. And we have shown, I wrote at the end, and if you listened along with the video, we explained why the number we got was as high as possible. It had something like 11 or 12 digits, something like that. We can go back and count. I'm not going to. But we definitely have the largest positive integer that satisfies these conditions. So we're done. It was a nice question. You know, there's not a whole lot more to say about it. You definitely have to know your primes. And once you knew your primes, it was then sort of a matching game. How many 3s at the start can we match up with 3s at the end? How many 9s and so forth? And that really, once we made that connection, that really forced the number on us. And after that, it was just picking the largest available number. So I hope you guys enjoyed that question, and I hope you enjoyed all of Part A. And in the next video, we're going to move on to the start of Part B, question number 1. And then we'll continue on with 2014 in the next video. So thank you all so much for watching.